Is there any music? There is no music, Pak.
Oh,
I
yeah?
didn't share anything. Is it from your earphone? No?
No, not at all. I'm not sure why. Why is there any music in here? Seriously. I thought it was music. Seriously.
No, sir.
I
I didn't share anything.
So what is this? I'm not sure. I don't know. Maybe from the student.
I think it's fine with my Zoom.
Okay. My mistake because sorry. Actually, I did experiment. Okay, really sorry about that. I did experiment remotely, and my students in their side. Okay, he turned on the music. So I was panicking. Why is there any music in here? So yeah, really sorry about that. I had to do many multitasks. Let's start it now. Okay, I'm gonna start this class today. Okay. So we have reached our very last chapter of this class. Okay, and actually for the mixing is mostly useful when you are doing scale up. Okay, and for calculation itself in mixing, only two aspects. First is heuristic aspect, okay, rule of thumb aspects, and the second one is actually it's more complicated. It's more related to the computational fluid dynamics. Okay, not everyone. Actually, when we are doing mixing, okay, we don't really have any capability or any detailed knowledge about what really happens in our equipment. It's more like we don't know, but somehow it was mixed quite well, something like that. Okay, so what will I give to you, or what will be given to you by me? It's about the estimation and then your sense. Okay, your logic. It's more like your logic. Okay. Now when you see, I'm not sure, but during this semester, I always get the very last chapter of many classes. Okay, so I always get too many. So maybe for the fluid mechanics, I have my part is this mixing and non-Newtonian and something like that. So yeah, it's more like estimation. Okay, mixing. Anyone wants to state his or her opinion about what kind of imagination? Okay, what can you imagine when I say a mixing word of mixing? What does it mean? Anyone wants to answer? Mixing. Brian, sure.
I would like to try, sir. It's about agitation.
Agitation? Possibly. Okay. Another. Mixing. Yeah, mix up. And we are doing mixing means we want. Okay, Azra.
Yeah, I think for me, just a simple explanation is when you add two or more stuff together, add two or more different stuff together.
And then you want them to get mingled. Okay.
Yeah.
That's it. So I don't really, even when I was student, I don't really understand about complicated such complex definition. So mixing is just your involvement, okay, towards your mixture so that it can be mixed much quicker compared to natural mixing. Okay, this is just because you wanna get involved. Okay, so that your mixture can be mixed. Okay, can be mixed quickly. That's all. Okay, so scope. Okay, so I want to tell you maybe certain information about the effect of impellers and use of mixing in industries. Then estimation of required. Okay, say this one is estimation, so never detailed calculation, but nevertheless you need to calculate that. Okay, and then the instructional purpose of this module is a comprehensive understanding of mixing process and its usage during scale up or scale down certain chemical plant of certain chemical process. Okay, because I think you guys also have had the introduction of chemical engineering. Okay, TK2107. Okay, it was said that there are two types of continuous reactor. Okay, first is plug flow reactor, and the second one is what? Continuous stirred tank reactor. Okay, but in many cases when we scale up those processes, we are facing what can I say, performance deterioration. Okay, performance decrease. Okay, when we are scaling those chemical process, okay, up. Okay. Scale up is always problematic. Why? Because we never understand. Okay, we never really knew what really happened. Okay, when the scale, okay, inside our reactor, inside our vessels, we don't really know it. Okay, unlike in your lab. Okay, when many people said yes like this. Okay, chemical engineering, okay, or process engineering is always related to the big scale. Is not entirely correct, because process engineering is also related to the lab scale experiment. Okay, and those lab scale experiment needs to be commercialized. Okay, you have, suppose a reaction here. Suppose you want to produce certain type of enzyme. Okay, enzyme is expensive. Okay, but you have maybe this one is micropipette and this volume is maybe 0.5 microliter, and you get 100% conversion. Okay, but you cannot sell this one. Okay, you don't know how to sell this 0.5 microliter. Do you think this one is an anti-material? No, we need 5 liters of the enzyme. Okay, you need to scale up to 5 liters of the enzyme. Okay, so you need to consider about the geometry of your reactor, geometry of your bioreactor, suppose. Okay, because when you are doing your reaction, okay, so why do I always take the example of chemical reaction engineering or chemical reaction? It's not because that I'm from the chemical reaction engineering lab or no, it's not because of that, because the scale up is always problematic in the reactor. Okay, for the separator is not quite difficult. Usually it's like that. Okay, for the primary mover such as a pump or compressor is not that difficult. It's not that problematic. Real problems, okay, always happen in the chemical reactor. That's why we need to study about this chapter. So let's imagine you want to sell 5 liters of enzymes. Maybe this one is 0.5 microliter per day, and you want to sell 5 liters per day. Okay, what you need to do? Okay, you need to check whether the requirement of your reactions are already fulfilled by your setup. Okay. Usually in our lab scale, this one is called a lab scale, and this one suppose is industrial scale. In the lab scale, we always give our best to provide our reaction. Okay, it's always overwhelming one. Okay, it's always overpowered. Suppose you need and suppose 0.5 microliter. How can you check the temperature? It's simple. You just need to bring it into the incubator, 40 degrees centigrade. That's for the temperature. How about its mixing? It's also easy. Do it with shaker, because the momentum given by shaker is more than enough to mix your enzyme inside this micropipe, I don't know, microchip, suppose. I'm not really remembering those things. But what if your reactor now has 5 liters? 5 liters is big, isn't it? Now, how about its temperature distribution? Okay, will you use jacket here? Okay, jacket. Okay, or will you use coil in here? Something like this. Okay, it's also a field of the study. Okay, and even though you are studying, when you studied in chemical engineering, mostly maybe 80%, more than 80%, okay, it's related to the equation, but those equations don't appear by themselves. All of them do appear in the lab. Okay, that's why this scale up, maybe we need to, from the lab to the pilot to the industrial. That's why we need this pilot. We need this pilot scale experiment to really see what happens when we increase the scale, maybe 10 times, 20 times, till 100 times. And then we can predict it. Okay. And the mixing, okay, even though you are now not mixing enzyme, and it also actually it happens in many reactors. In CSTR, okay, when our mixing okay don't work very well, usually the conversion is going to be reduced. That's the fact. Okay, especially when we are scaling up PFR, it's much more difficult. Okay, I'm not gonna share my problem with you, but it's more difficult compared to lab scale one. Okay, that's why this one, okay, aside from giving you the mixing estimation study, I also want to deliver the scale up aspect in chemical engineering. Okay, so why do we need to study this chapter? Because we need to scale up. Okay, and scale up activity is something that you cannot avoid. Okay, even though you are very excel in the lab, and also you are also excel in the calculation using process simulator, suppose MATLAB, HYSYS, Python, anything else. But when you don't have any pilot plant data, nobody will buy your process. That's the hard fact that you need to understand. That's the process. Okay. Okay. So that is why you need to study this thing. Okay. So mixing process, okay, are related to many things. Okay, actually, from the solid dispersion, fluids mixing as the most common one, and then molecular mixing, and then emulsification, mixing in the pipe. This one is called a static mixer, and then solid suspension mixing. Anyway, here today we are only going to study about the fluid mixing. And as you can see at the right side picture, right side animation, okay? So there are two aspects in here. First one is the estimation. We will study it later. And this one is detailed simulation. And this one is using CFD, computational fluid dynamics. Okay, even though we are using CFD, we don't really have any capabilities to predict what happened. Actually, we just have the capability of interpolating what happened, what did happen. Okay, only interpolating, not extrapolating. Okay, we just know how to rationalize our results. Okay, suppose this reactor, this scaled up reactor conversion is getting lower. So what happened? We change the variable in the computational fluid dynamics and then find out, okay, this maybe probably happened. Maybe our turbulence is less than what we required. Okay, only that. Okay. Other than that, we can only estimate. But please, even though the name is maybe, even though it's called estimation, but do estimation accurately. Because when you do your estimation accurately, your industries, your boss, maybe, or your supervisor will be very happy with it. Okay, because you can save their money. Okay, that's all. Okay, so this is the background about the mass transfer. Okay, actually, you can find it in the book of Nevers, Noel de Nevers, chemical fluid dynamics for chemical engineering. So for certain organic substance, okay, when we have separated distance, okay, separation distance is around 1 centimeter, and you have this diffusivity and separated with this one. Actually, if the film thickness is around only 1 centimeter, we need 200,000 seconds. Okay, actually this skill, okay, this knowledge is gonna be reminded to you when you are entering the class of transport phenomena. Okay, and maybe in the next year. But let me remind you, okay, that if we don't mix, if we don't disturb it, suppose we have 1 centimeter film length. In order to get completely miscible mixture, we need around 200,000 seconds for this fluid. Okay. Okay. What if we have 1 meter? What if we have 10 centimeters, suppose? So it's going to be hours, days. That's why we need to disturb them by destroying, not destroying, by disturbing the film layer, by disturbing the film layer, by giving external forces in the form of mixing. Okay, this is the background. Okay, if you don't mix it, it's gonna be very long. Okay, it takes almost a year, suppose. I mean, it's gonna be very long. Okay, so like your friends, like been said by your friends before. Okay, mixing is about the agitation, so actually it's not quite same. Right? Okay, agitation is not strictly same with mixing. Okay, agitation is the flow manipulation in order to create certain flow pattern. But mixing, we want to create turbulence. Okay. Okay, so these two are very extreme example. First, we really want mix. And this one, we only want agitated. In the CSTR, we really want to have very high Reynolds numbers. Why? Turbulence, okay, has us to mix our reactant with catalyst or reactant or reactant with the other reactants much quicker compared to non-mixed one. Okay, so in the CSTR we use high RPM and we use baffle, and we really try to increase its turbulence, its Reynolds numbers, because yeah, when we have very high Reynolds numbers, means it's very intimately mixed and it can help the reaction to proceed. But the other extreme is wastewater treatment. I'm not sure whether this one is called as the primary clarifier or whatever. You can ask Pawawan. Okay, okay. So in the wastewater treatment, okay, usually clarifier is like this. Okay, something like this. Okay, and this one is inflow and somehow it's outflow, and this one is the sludge, if I'm not wrong. Okay, and in this case, the dirty water, this one is dirty one, is mixed with coagulant. You know coagulant? Okay, coagulant means a substance, chemical substance that can increase the particle size of your suspended solid. That's all. I'm not sure in aluminum sulfate. Okay, in bahasa it's called tawas. Okay, when I was still maybe junior high school and high school, I came from Bontang. Okay, that city has very bad water quality, and back then my daddy, my father, gave this coagulant to precipitate. Okay, to precipitate the dissolved iron, because the water smells very bad. Okay, and we want this precipitation not to be disturbed, because when it is disturbed, the particle size is gonna be bigger. Sorry, it's gonna be smaller again, and the water is not gonna be clarified. Okay, so in this case, you cannot use very high RPM. Okay, you just push this pedal mix, no, maybe pedal impeller. Okay, you just need to move it slowly so that the pattern, okay, so that the heavy one can go to the bottom part, and the light one, means the clean water, okay, goes on the top side. But we don't want to create any turbulence in this one, so that's why it's called as an agitator. Okay, something like that. So by definition, it is like that. Okay, but somehow when you are working, it might get quite messy. I mean, it might get interchange. But more appropriate definition for agitator, you don't need to create high Reynolds number. You just need to push the liquid, okay, push the fluid into some certain pattern of flow. Okay, that's all. Okay, so like I said to you before, you have learned about the Reynolds numbers, but now in the agitating, okay, mixing or agitating or anything else, there is a thing called a power number. So power number is a certain number that correlates between required power in here with resulted turbulence. Okay, so always when you did the calculation of friction, you need to find at the very first step is the Reynolds number. It's gonna be the same for this mixing. All you need to find the Renault, but it's not usual Renault, it's the Renault of your impeller. Okay, so actually this one is rho u d over mu, but the u here or v here is translated as the amount of the RPM multiplied with the diameter of your impeller. Okay. Okay, so it's gonna be like this. Like you studied before, Renault is different from case by case. Renault of the fluid, Newtonian one is easy, isn't it? Okay, rho v or u d per mu, something like that. But what about the Renault of non-Newtonian fluids? So it's going to be more complicated because the mu is not the same for every cases. Okay. Okay. So and this power number correlates when you find the Renault. Okay. Very first thing is always you find the Renault. Okay. After you get the Renault, you need to fix which type of impeller you are going to use. So this curve is going to be different case by case, impeller by impeller. Okay. Okay. And this curve is acquired from what? From experimental. Okay. You cannot stay in your room and then devise and then you devise everything and then you can get this curve. It's impossible. Okay. You want to go to the lab in order to get this Renault. I mean, sorry, this is power number characteristic. Okay, and then after that you find out which curve, which after you get the Renault, you need to find which impeller. Okay, after that you get, sorry, why always like this? Okay. Then after that, you get the power number. After you get the power number, then you get the power required in order to mix your mixture. Okay. From this part, is there any question? Because this one is the essence of this class today is located at this graph. Okay. From this graph, I think up to this point, is there any question? Still good? Understand what this one? Do you understand what it? Oh, no or yes, or you are not sure whether you understand or not? No or yes, student? Oh, come on. So I take it as yes, possibly. Okay. So the Renault, okay, the Renault, after you get this Renault, you can get this power number. After that, I mean, for this usually it's like that. Okay. You need to find first. Sorry, I need to clarify. You need to find what kind of impeller that you are gonna use first. Okay. How to find what type of impeller? You ask the others or ask internet. I mean, ask your peers. Suppose. I mean, it's gonna be different case by case. Suppose for the pedal, okay, pedal type, it's very good for viscous fluid, but for this impeller, sorry, for propeller type, it's very good for non-viscous, such as water. Okay, so you need to find which impeller is the best for your case first. After that, you fix which graph is there. I mean, which graph is going to be used. Okay, graph 1, 2, 3, 4, 7. If suppose your impeller is in this graph, and then after that you try to calculate the Reynolds number by using this one. Okay, suppose 1000. Okay, and then suppose you are choosing graph number 7. Okay, something like that. Then here you get the estimated power number. After you get the power number, you can estimate the power use. Okay, okay, you get it. Okay, 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 something like that. But first thing comes first is about the type of the impeller. Okay, you need to ask your peers, ask your vendor, ask your boss, ask your friends, which one is the best one. Okay, we can only give you the rule of thumb, but it's just gonna be different case by case. Okay, okay. So I give you the power number calculation example. Okay, certain type, maybe I'm choosing the type number 1 because yeah, I'm just choosing this one arbitrarily. With this D like this. Okay, and then D of the tank is something like this. Okay, and then at 240 RPM, this means 4 rotation per seconds. And estimate required power to conduct this agitation or this mixing operation. So very first is always choosing which type. Okay, type 1 means this one. Okay, so I said to you, in order to determine which type, you need to ask. Okay, don't or maybe if suppose you are finding yourself within an exam situation. Okay, during the exam, we will not ask you to we will not ask you to arbitrarily choose which impeller is the best one. Okay, we will give you the data. Okay, maybe we just give you the rule of thumb, something like that. I mean, for any case 1 till 7 case, you need to ask. Okay, you don't want to suddenly have an idea. Okay, I'm gonna use number 5, something. Who said so? Okay, it's gonna be different, suppose. Okay, and in this example, I use number 1 because I just arbitrarily chose number 1. Okay, then I choose, and then after I chose number 1, I calculate its Reynolds. Okay, this one. Okay, this one is the diameter of impeller. Okay, 0.2 square, 0.04. Then you get the Reynolds 17,000. Okay, 17,000 means around here. I'm not sure. You can use because this one is log versus log, and then the maybe around here. I'm not sure. And then from the graph, maybe I wrongly read this one. Maybe from the graph, the power numbers maybe 5 point something or 7. Maybe this one is not quite good because I wrongly chose the graph at that time. I'm really sorry about that. But the power number is maybe around 7. Okay, maybe it's around 7. I'm not sure because this one is log versus log. Okay, and then after you get the power number, you can calculate the power required. Okay, then you can estimate. So estimated power required in this operation is going to be around 82 watts. Okay, if we use this one to mix this one, but please, this one is not quite correct. You find it by yourself. Okay, what kind of, okay, I did not realize that my eyes was wrong. Maybe the power number is going to be around 7. Okay, so if we have power number equal to 7, then you can get this one. Maybe if it is 7, then maybe it's going to be around 160 watts. Okay, Can you follow me? Okay, because my eyes did not work very well, so maybe 17,000 corresponds to power number equal to around 7. Okay, sorry about that. Then you have 160 watts, something like that. But suppose my eyes were correct. Okay, for time being, let's assume that 82 watts is correct. Okay. Okay. Any question up to this point? Anyone? Any question up to this point? No? No question? Clear? Understood what this thing? Okay.
Sir, sir,
Yes.
I still confused. What is N in the RE impeller, sir?
Hmm?
What is N in the
N.
Yeah.
That is the RPM.
Oh, okay.
Sorry, RPS, rotation per second. Okay. So if I have 240 RPM, means what? 4 rotation per second, isn't it?
Yes, sir.
Okay.
I understand.
Okay. 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 Let me give the indication here. This one is, sorry, this one N is RPS. Okay. In order to find the Reynolds. Okay. After you get the Reynolds, then you can get the power number, resulted power number by certain type of impeller. After that, you get the required power. Only that. Okay. Only that. That's the first thing. In order to estimate the use power. And then this one, anatomy of impellers, or actually mixing system. Okay. When you mix it, actually, you live in Indonesia. Okay. I give you really hard facts actually. Okay. When we are dealing with mixing system, with scaling up in Indonesia, usually your boss don't really care about the geometry of your tanks, of your impellers. They don't really care about it. So usually when first 5 liter per second, you need volume of 10 liters, suppose. Now we are going to handle 500 liter per second. So maybe we need V equal to 1000 liters or 1 meter cubic. That's all. They don't really care about this one. They just push their volume to you. Okay, we don't really care. But when we are scaling up, when we are scaling our process up, we need to take care about this geometry. Why? Because most possibly when we give the same geometry, then the height rheology, okay, rheology is going to be quite similar. Okay, that's it. But when you live in Indonesia, okay, your boss, okay, your vendor or your supervisor don't really take care about this one. So when you have power, okay, to change, or when you have power to design, please take care about the similarity of its shape. Okay, you need to take care all of the ratio. Actually, that's okay. And another thing, there is a thing called as a baffle in here. Baffle is greatly used to increase the Reynolds number. Even though when you use the baffle, the power consumption tends to be higher. Okay. Okay. Only that. This slide only contains two information. First, the anatomy of impellers means the similarity, the similar ratio, same ratio must be kept in order to scale up your tank. Okay, so that you can get similar Reynolds number, because we need to take care about our degree of turbulence, something like that. Okay, especially during the reaction. But it's not ideally enforced, especially in our country. Okay, and second one, there is an equipment that's called a baffle. Okay, this equipment is used to increase the Reynolds number by creating turbulence. Okay, okay. So actually, really sorry about that. Why this is like this? Really sorry. Okay. Okay, let me explain to you about our rule of thumb. So actually, there are three big types of impeller. First is propeller. Propeller is simple. Propeller is like your marine propeller, or it's like propeller for the ships. Okay, and it's very good for viscosity less than 3000 centipoise. Okay. So for water, for apple juice, something like fruit juice, it's good. But when the viscosity is increased, okay, we need to change our option. We need to change our impeller selections. We can use turbine. Okay, this one, this middle turbine. Turbine is like turbine. Okay, and then if we have higher viscosity, okay, we need to change it into pedal. So pedal is used for viscosity higher than 500,000 centipoise. Okay, so if we have viscosity, okay, if slow viscosity is propeller, and then quite higher turbine, higher viscosity pedal. Okay, so what is the shape of pedal? Okay, you must remember our beloved ice cream pedal pop. Okay, pedal means something used to pedal your boat. So pedal pop, okay, is ice cream that is shaped like a pedal. Okay, it's like that. Okay, pedal is like that. So if you still want to remember what type of ice cream do you have, is pedal type. Okay, pedal is something like that, or something like simple, very big, something like this, but with big something like this. Okay, this one is pedal, and this one is the axis, and something like that. This also can be called as a pedal, and it also can be called as a pedal. And when you have very high viscosity, it's almost impossible to give any turbulent flow. Okay, even though you increase its speed of mixing. Okay, so usually when we have very high viscosity, it's not called as mixing anymore. It's more called like agitating. Okay, and like as I said to you in this before, baffle is not needed for viscosity higher than 5,000 centipoise. Why? Even though we put the baffle, when the flow is really viscous, is highly viscous, it has no use at all. Okay, so the existence of baffle in here, suppose this one is the cross section from the upside, okay, and this one is your mixer, something like this. If we have low viscosity, let me give another color. Okay, the baffle will, if suppose we are rotating it clockwise, the baffle will give micro turbulence, micro vortex in here. Okay, something like that. Thus, when you have 2 or 3 vortexes inside your tank, the flow will be more turbulent. Okay, but if you don't have baffle, usually it's just like this. Okay, this is the mixing, something like this. So the vortex will be created, and vortex, okay, is not same with turbulence. Vortex is just a laminar flow inside circular tank. Only that. Okay, so when you mix your tea, okay, when you use very high speed and then the vortex is created, means your tea was mixed inefficiently actually, because when the vortex is created, means the regime in your impeller, okay, is a laminar one. Okay, you don't want to create it. Okay, that's why we fix baffle, okay, to break our flow. And as you can see here, like I said to you before, the use of baffle, okay, for the same type of impeller, increase the energy usage. Suppose this one is the power number for the same Reynolds. Suppose the Reynolds is maybe 2000 here. Okay, there is an energy gap in here. Okay, as I said to you before, the power number gap. When we don't use baffle, maybe the power number is around 0.8, but when we use baffle, okay, the power number is going to be around 1. So the use of baffle is always, it has its own drawbacks. So as I said to you before, in many students, okay, in chemical engineering, especially in fluid mechanics, there is a trade-off, always a trade-off like this. This is a seesaw effect. First is the performance of mixing, and this one is dollar, or maybe energy. Sorry, not dollar. Sorry, really sorry about that. This one is the energy. This one is the power. Okay, you cannot get both of them simultaneously. You need to sacrifice one aspect in order to get another aspect. Okay, that's chemical engineering for you guys. Okay, you need to adapt. Okay, let me stop share for a little bit. Let me share this one. Okay. Okay. Oh, what happened in here? Okay. Okay. Let me turn on my video. Okay. Can you hear the sound of the video? Hello? Can you hear the sound of the video?
Yes, sir.
Okay.
Finally, we will demonstrate an alternative to angled off-center positioning of the mixer. In some applications, or certain types of mixers, it is not possible to angle the mount off-center. In these cases, we recommend installing anti-swirl baffles in the tank. Typically, we recommend 3 or 4 baffles equally spaced. However, in our demo, you can see that even introducing a single baffle will effectively eliminate the vortex and create a uniform mixing result. Just as with proper off-center positioning, adding baffles creates a uniform hydraulic load on the mixer shaft, which will provide maximum mixer life.
Okay. 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 Where is mean? Okay. Okay. So as I said to you before, the use of baffle, okay, like this. Okay, really sorry about that. Okay, where is it? See, what is this? This one is called as vortex, okay. And as you can see here, this one is the mixed substance, suppose, okay. Okay, it happens not efficiently, okay, because this vortex, okay, this vortex is a laminar one, and then it tends to keep, because when you have laminar flow, okay, suppose in the pipe like this, okay, in laminar flow, okay, each layer is not supposed to disturb another layer. That's the secret of laminar. Okay, layer 1, layer 2, layer 3 till layer n in here. Layer 1 is not disturbing layer 2 because it is laminar. That's why we don't mix anything inside a clean pipe. I mean, inside a pipe, we cannot really mix it except we put something inside the pipe. Okay, so this vortex is bad because this one indicates the laminar state of your tank. Okay, and then this laminar state means inside the laminar regime, any of your mixed substance is not mixed well. Okay, that's all. Okay, so this one is the mixing pattern. During mixing process, the mixing pattern should at least, there are two patterns. Okay, there should be at least two patterns. First is the radial ones. Okay, something like that, and then the axial one. Okay, when we scale up our reactor, suppose we have very tall tank. Okay, usually one impeller is not enough. We give 2 or 3 impellers in here because the radial in here is not enough to create rapid axial mixing in here. Okay, so don't be surprised in our chemical plant. Usually there are multiple impellers. Okay, something like that. So mass transfer limitation and mixing. Why do I always call this one? Because it's somehow it is problematic in the term of reaction engineering. But please don't be afraid. Okay, I don't want to join chemical reaction engineering because it's difficult. No, it's not like that. Usually we do many things by trial and errors, and then we do rationalization after that. Okay, suppose this one. Okay, when you don't mix it, your reaction will your mixture, okay, your mixture will be ruled by mass transfer limited regime. Okay, this one means the in this step, okay, in this region, your catalyst is being bottleneck. Your reactant is being bottleneck. It's like this. When you go to do your lunch, when like this, what is the speed? Okay, what is the speed of serving in the McDonald's or in any fast food restaurant? I hope you are hungry. Okay. How many minutes can you get your ordered meals in the McDonald's, suppose? 15 minutes? 30 minutes? No, usually it's under 5 minutes. So if this one is the McDonald's, okay, and the reaction is it can be if I want to measure how fast you eat your meal, I can just measure. So suppose in at 9:03, out at maybe 9:15. Okay, this one is the apparent if the McDonald's is not crowded. But what happens if the McDonald's is crowded? You go at 9:03. Okay, sorry. When McDonald's is crowded, enter at 9:03, and then you can come out at 9:45. So I cannot say that this 42 minutes is your rate of eating. Okay, no, I cannot say it like that, because it is well located inside the mass transfer limitation regime. Later on you will study. Okay, if suppose you meet me in chemical reaction engineering, I will teach you this one. Okay, so what will we do? Okay, we need to get involved, okay, by giving external force, so that the mass transfer limitation regime can be reduced significantly. And as you can see here, if suppose you are in McDonald's, okay, and people are crowded in here, what can I do as the owner of it to increase the rate or the turnover ratio of your McDonald's restaurant? It's simple for me. I'm just gonna put, what can I say here? How if I put a dog, or how if I put a police? How if I put a certain person, okay, who are not liked by our customers? Our customers like our meals, but our customers will not like our restaurant. So this is the analogy. Okay, so most of our customers will take out order instead of dine in order. Okay, so the speed of eating, okay, or the speed of serving will be controlled by the skill of our clerk, of our servant, sorry, or waitress, sorry, not servant, chef and waitress. Okay, okay, so it's going to be the same when you are dealing with scale up. The scale up of any reaction or any reactor, usually we need to increase the RPM, okay, but somehow at some point when we increase the RPM of our mixing, it does not increase the reaction rate significantly anymore. Okay, so we keep this as our optimum RPM. Okay, that's why we need to use scale up study in order to determine which RPM is the best one. Okay, it happens actually, and we need when we have entered the kinetic limited, we don't need to waste our money to increase the RPM, because when we increase the RPM of our impellers, means it will consume more energy. Okay, that's it. That's the logic actually. Okay, so you let me skip a little bit. Okay, geometry, kinematics, and dynamic similarity. And let me skip to this approach. Okay, when you increase the scale, there are two aspects. First, completely copy the Reynolds number. Okay, completely copy the Reynolds number. So in the example at the 7th slide, what happens if I increase 2 times larger? So it was increased from 82 watts into 3000 watts, 40 times. Okay, when we insist to take Reynolds as the, I mean, when we insist to fix the Reynolds number. But another aspect can also be used. Okay, we can use the P over V ratio. Okay, by using this approach. Okay, the Reynolds will be smaller. That's the eventual result. But after that, we can get lower. After that, we can get lower power consumption. Okay, so there is a misconception when you are increasing from the 5 milliliter into 50 liter. Okay, people just use, okay, let's make the RPM same. So here suppose it's 1000, let's make it 1000. Okay, but this similar RPM doesn't really result, okay, same Reynolds. Okay, like I said to you before, somehow when we have very tall tanks, there are several impellers in here, something like that. Okay, in order to create similar Reynolds numbers. But yeah, that's it. Okay, there are two approaches that can be used. First is completely create same Reynolds number. Okay, and the other is completely, I mean, using the P per V. Okay, you need to recalculate the power per volume. Okay, as I said to you before, it does not really, I mean, both of them are not the best ones. I mean, you need to these two are only the estimation, but you need to study your pilot plan activities more thoroughly. Okay, especially in this power consumption. Okay, and then you can decide it later. Okay, and yeah, that's why pilot plan study is important, because from here to here, you cannot just cut and paste and then enlarge. It's not like that. So you need to use pilot plan first. But after you use pilot plans, even you need to find out, okay, whether the Reynolds are same or this P per V are kept for any ratio, for any scale up ratio. But for me, I'm not sure. I don't know which one is the best one. Okay, you need to find out anything like this, like this one. Okay, usage of missing in CSTR. You need to find it like that one. That's why the cost of product development is not cheap one. Okay, it's very expensive. Okay, you can use this one. Okay, you can use this exercise to train yourself. Okay, to okay, to scale up. Okay, so if you are scaling up, okay, from 10 liter to 10,000, that means 100 times. Okay, so it has height to diameter L per D ratio of 3. Sorry, bad drawing. Okay, L per D, something like that. L per D, okay, equal to 3. Then impeller diameter is 30% of the tank diameter. So here, if suppose it is 1 meter, then the impeller diameter is going to be 0.3 meter. Okay, and then agitator speed is 500 RPM, and 3 rational impellers are used. Determine the dimensions of the large fermenter and agitator speed. For constant P per V, okay, constant impeller tip speed, and then constant real knot number. Okay, you can assume geometric similarity in this one. Okay, you can actually is quite simple. You just need to find out which which aspect needs to be taken. Okay, it's not that difficult. Okay, it's not super. Constant P per V. Okay, for constant P per V means this one. Okay, okay, so small fermenter 80 liters energy. Okay, but production fermenter is 10,000 by 1. Okay, you need to find out what is this one, dimension of the large fermenter. Okay, so the dimension, you can find the dimension by using similar ratio. Okay, similar ratio. Okay, yeah, this one is only for the energy of impeller, but you need to find the similar ratio. Okay, and then constant impeller tip speed, you can go back in here. Impeller tip speed means this one. Okay, okay, so if the energy input for small fermenter is 1, it's going to be 25. Okay, 25 times, something like that. Okay, and then what else? Constant Reynolds number. So this one is going to be very last of this table. Okay, table, constant Reynolds number. Okay, then you can get the energy, something like this. Okay, but anyway, it depends on, I mean, when we are scaling up, it depends on our fluid and our type of impellers. Okay, here we can see that same Reynolds number will be applied. But yeah, for me, for more important for you is to find out its dimension. Okay, dimension is easy. You can use same. You can estimate it by using same. What can I say? The same ratio. Okay. 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 As I said to you before, there is no perfectly rigid rule, for mixer scale up, even those ones cannot just blindly increase the dimension impellers during the scale up, the dimensions of impellers, sorry, during the scale up. So you need to find out from previous studies. Okay. Then mixing efficiency cannot be accurately predicted by using known equations. Frequently use of pilot scale can predict the energy usage and mixing efficiency more accurately. So in your third year, you will need to attend instructional lab. There is a mixing tank module in there. And that in that mixing tank module, you are taught to correlate the power and power use versus T of mixing, something like that. Okay, only that. Okay, power use and V, and then you can see it. Okay, that's it for today. Okay, I don't have many equations to be given to you because it's more like rule of thumb approach. Okay, for me, it's very important for is for me the thing that has that needs to be prioritized is the sense that you use. I mean, when you scale up your process, you need to find similar approach like this. Whether you are gonna use constant P over V, constant RPM, constant tip speed, or constant Reynolds. I mean, that's all. And you can see in here, when you are using constant Reynolds, somehow in this scale up parameters for this equipment only, okay, somehow it has lower lower power, lower energy input. Okay, and furthermore, okay, when you are using a scaled up tank, scaled up reactor, you need to take care about the shear stress to your substances. When you are working with bacteria, it does not like to be mixed very vigorously. And also when you are working with some type of specialty products such as catalyst, okay, enzyme, something like that, it's not simply increasing. I mean, when we are simply, we need to study more in our pilot plant activities. We cannot say that, okay, let's keep the RPM same. So it's not going to be beneficial for your products, okay? Because your products somehow cannot withstand the shear stress very much, because your impeller creates shear force actually, okay? Your impeller is not creating pressure force. Your impeller is only creating the shear force, but when just shear force too much, okay, somehow some types of cells will be destroyed. Okay, it does not like, okay, something like that. And if suppose you are interested in any bioprocess product, or any specialty products, usually we don't use very high RPM. Okay, even in wastewater treatment, we don't use high RPM because the shear stress or shear force can destroy, okay, can break the coagulated material. When it is broken, means clarified water can get dirty again. So I think a lot of aspects need to be discussed before you scale your product up. Okay, you don't just go there blindly, something like that. Okay, up till this point, is there any question?
Sir, can I ask?
Sure.
So I'm still confused about the constant Reynolds number and the constant RPM. When do we know to use that when we scale up the mixer?
It's case by case. We don't know. I don't know. Seriously. Like I said to you before, this thing actually, why we need to, when you are scaling up aspiration column, this thing is not there. Okay, but when you are scaling up reaction, actually, we need to find this value by using experiment. We don't know. Okay, when you are using pilot plant experiment, you find this up, then you rationalize. Okay, that's it. Because because you don't use your grandfather's chemical plant, so maximum study, okay, maximum study that can be utilized by any process engineer is only pilot plant. So this is the lab, pilot, then predict. Okay, prediction means in industrial scale, because in industrial scale, the money stake is very huge. You cannot find this method by, what can I say? By experimenting 100 cubic meters of oil something. No, it's gonna cost very much. So here you need to from the pilot, okay, from the lab, you increase into the pilot, you can get the power number, okay. Then after that you can get the power, okay. After that you predict it, okay. In this pilot, okay, you use different approaches. You use Reynolds approaches, you use P per V approaches, you use similar tape, you use RPM, something like that. You check it actually. You need to check it, okay? Because beyond this point, okay, it's just a waste of dollar, okay? Waste of energy, waste of money, okay? Can you catch my explanation? Okay.
Sir, so how do we know which approach is appropriate then?
We use pilot plan experiment, okay. Then we try one by one, 1, 2, 3, 4, something like that, and then find the performance versus the energy. After that, okay, suppose this one works, this number 2 is working during the scale up, so we can predict. Okay, so we can use P per V approach for industrial scale. After that, we can predict the amount of energy consumed per minute, suppose something like that. Okay, but like I said to you before, when we mix it, I mean, this limit, okay, this limit can only be found by using experiment. Okay. So if you suppose you are just copying the RPM, it's okay, but you will waste money, lot of it, because somehow if we keep the RPM, maybe it is in this point, and then you waste the money. When you increase the RPM, when the RPM is because when you are dealing with experiment, especially reaction experiment in the lab, the RPM is always overwhelming actually, isn't it? I mean, I think you have never done any experimental activities yet, okay, for years of 2020, but when we need actually 100 RPM at the lab, we never use 100 RPM. Okay, we always use 2000 something, because we also want to save time, something like that. Okay, actually we can also predict this curve. Okay, we can also predict this curve in the lab. We can also predict it in the lab. We find out the mixing, okay, one by one. Okay, then use this one. But still, when we are scaling up, we never, actually the ideal scaling up, we never want to cherry pick. Okay, we never want to cherry pick one option only. We need to check many other options. Okay, in this one we check the option of constant P per V, constant RPM, constant tip speed, and constant Reynolds. Which one is the best one? Okay, if suppose for the constant Reynolds, okay, you have, and then because for this one you will have the X, okay, the performance of the reaction and the power, isn't it? Okay, you also XA power, XA power, XA power. You will have case 1, 2, 3, and 4. And which one has the acceptable conversion but the lowest power? Maybe option number 4. I'm not sure. Option number 4. Okay. For option number 4, we have the lowest. Maybe the conversion is matched with your needs. Maybe 95%. Okay, not 100%, but 95% is good. And here the power consumption is the lowest one. Then you use this one, okay, for the constant Reynolds. Okay, so when you are scaling this up, you click, I mean, you pick the constant Reynolds for your design chemical plant. Okay, you throw away these three. Okay, but in order to get which one is the best one, you need to go for the pilot plant experiment. Okay, so can you? Yes.
All right, sir. Thank you. I get it.
Okay. You got it. Okay. Yeah. So it's quite painful actually. We from the chemical reaction engineering lab, we have oh, why is it different? I thought the conversion would be 99%. So in the field, it's not even 90%. 5% difference means less money, and then we are also supposed to be responsible for our results, okay, to our funding agency or to our client, something like that. So yeah, that happens. Okay. Any other question? Any other question? No? Then if there is no more question, I think it's very, best option for us is to end this class today. Sorry if I have maybe if I skip some things. Okay, I'm really sorry about that. See you in the exam. Okay, hopefully you don't need to take the, what can I say, remedial exam. Okay, and I'm not sure. Third module exam, I'm not sure when will we conduct it. Okay, just be prepared for the third module exam. The exam material is, what can I say? I forget. Pawan, do you remember it?
Yeah. Can I add some pengumuman, Pak Haryo?
Okay.
Okay. So our last module exam, which is the third one, it will be conducted on next week. I think it's on Wednesday. Yeah. Just check your CX. I think it's already scheduled in CX. If I'm not mistaken, it's on Wednesday at 9 to 12. And it will be used for the ujian module 3. Yeah. So the third exam module. So after you did the third exam module, we will collect all your grades, and then we will discuss, yeah, among the lecturer, and then for the students that's the grades still below passing grade, which is C, then you will given one remedial exam. The time for the remedial exam is still tentative. I will contact the students later for the one that needs remedial exam. But for this remedial exam means the maximum grade that you will get is only to C, yeah, because it's just for increase just a bit below the passing grade until you can pass the passing grade. I think that's all. Any question about the exam?
Easy.
Oh yeah, the material for the ujian module 3 is particle, yeah, the basic of the particle, the application of the particle, non-Newtonian fluid, and mixing.
Okay.
Yeah, I know that's quite a lot of equation that you should use, but most of the equation is just some is the empirical formula, some is the rule of thumb, like Pak Haryo said. So just make sure what kind of the case that you need certain equation. Yeah, you have to understand when to use which formula for certain condition. You don't need to derive or etc.
And for the regular class, actually, I created assignment. Actually, I asked them to create a cheat sheet, acceptable cheat sheet. I mean, for this fluid mechanics until the end. So I think it's going to be better for international class member also do this exam. Actually, I haven't put in the EduNext yet, but I think we can put the deadline by tomorrow. Okay, So it's going to be better for you to create cheat sheet. Okay, I mean, very good cheat sheet, colorful, something like that, and please store it. Okay, keep it in your notes and use it for, I mean, maybe for during your career as a chemical engineer or process engineer. It's going to be important for you, even though those cheat sheets are not quite accurate yet, but the logic is going to be the same. Okay, so as I said to the regular class before, it's going to be better for everyone to summarize their materials till this time or one semester and create a cheat sheet, because you are going to need it later. Okay, not only in the exam. Okay, okay, only that. Thank you, Pak Wawan.
Okay, thank you, Pak Rio. Is there any question from student? Okay, if you don't have any question, then today is our last class, yeah, for fluid and particle mechanics. Thank you, Pak Rio. Thank you for the students. We are very sorry if during the session class we have lots of kekurangan-kekurangan. What is in English? Yeah, maybe
lot of things. Okay.
some unintendable mistakes. Yeah.
Okay.
Unintended mistakes. So I hope you can do the exam well, and we hope that the results for the grades is also good for all of you. Okay, see you in the exam. Thank you again, Pak Rio and student, and very good morning.
Okay, bye-bye.
Thank you, sir.
Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you very much, sir.